Well, as I promised, I'm going to do this practice final exam, and I hope that everyone has already worked it through, and you can see whether your answers agree with mine. And I'll explain what I had in mind when I wrote these various questions. As an undergraduate, probably the single most useful class I ever had was when Wendell Furry, who was teaching a year-long graduate course in electrodynamics, gave back the exams for the first half of the course and explained what he'd had in mind with each question, because it had never occurred to me before that any thought went into constructing exams. So for those of you who are interested in teaching or who already teach and want to compare notes, this might be interesting, even if you've got all the right answers. And I should say, someone got 100% on this exam last year. Someone got 49 out of 50. He already had a master's degree and was going into a PhD program. And the third person got 92%, and he was just admitted early decision to Brown. So if you're in the 90s in this exam, you're in really good company. And if you're 70 or better, you're in perfectly reasonable shape. Okay, I'm going to work the multiple choice items first. And one of the secrets of doing multiple choice items, I would say, is work the question and then see whether you got one of the answers. Don't try to work backwards from the answers and try to guess which one has to be correct, particularly if they're all numerical and arranged in ascending order. So the first one looks to me like an inclusion-exclusion question, because we have three events: a red card, so this is question 1, which I'll call R, and the probability of getting a red card is given as 0.6. The probability of getting a red face card is 0.32. That's the probability of R intersect F. And finally, the probability of getting a card that's either a red card or a face card is specified to be 0.8, and what you're supposed to figure out is the probability of a face card. Well, this is a backhanded inclusion-exclusion question. There are 4 items included in the inclusion-exclusion principle, and we're given 3 of them here, though not the usual 3. So we can start with P of R union F equals P of R plus P of F minus P of R intersect F, and put in the numbers. We've got 0.8 equals P of R, which is 0.6, plus P of F, which is unknown, minus P of R intersect F, which is 0.32, and therefore P of F is equal to 0.8 minus 0.6 plus 0.32, which is 0.52. And one of the nice things about multiple choice items is if you make a really stupid mistake in arithmetic, you'll get an answer that wasn't included. Here, 0.52 is there. It's choice C, and that's the right answer. Questions? Okay, I'll move right on to question 2 then. Somehow I don't think I'm going to make it through the exam with that marker, though. Let's try old reliable red.
It's very difficult to see.
That's okay. Okay, this is question 2. A craps question. You roll a total of 5 with your 2 dice, so your point is 5. Now you keep rolling the dice until you again roll a 5, in which case you win, or a 7, in which case you lose. What's your conditional probability of winning once you've rolled the initial 5? Well, I'll denote by S5 and S7 the probability of rolling a 5 and a 7. And the question is, given that the roll is either a 5 or a 7, what's the probability that's 5? There are lots of ways to do this problem, but this is probably the simplest. Well, the probability of a 5 is the 4 ways of rolling a 5, which are 1, 4, 2, 3, 3, 2, and 4, 1 over 36. Probability of rolling a 7 is 6 over 36. And this probability is therefore equal to 436 divided by 436 plus 636, which is 4/10 or 2/5. And I would think it would be entirely reasonable to look at this one and say there's 4 ways of rolling a 5, 6 ways of rolling a 7. Nothing else matters. That's 4 out of 10. You can do it in your head. This is a little more formal. Questions about this one? And as I hinted last week, these questions may have appeared on the practice exam because there was a matching longer problem on the exam that you're going to get next week. 3, boys and girls. Family has 10 children, 7 boys and 3 girls, and you want to figure out the probability that there were always more boys than girls in the family. You spot this as a ballot theorem question if you say, oh, that's the same thing as there are 7 votes for candidate A, 3 votes for candidate B. What's the probability that candidate A is always ahead? Or Harvard and Yale play 7 football games. Harvard wins 7, Yale wins 3. What's the probability that the games were played in such an order that Harvard was always ahead? So this is just one storyline for a ballot theorem question. And here's what we've got. We've got excess boys plotted against the number of children. So the growth of this family is a random walk where a boy counts as a step in one direction, a girl counts as a step in another, and after 10 steps, there are 4 more boys than girls. And never after the first birth is the number of children of either sex equal. The ballot theorem says level gain of 4 over number of steps gives you the fraction of the paths that have that property. Questions? Okay, well, we're breezing right through this. Okay, number 4. This is a generating function question. And I've already given you a pretty broad hint that the only generating function questions that I'll put on a final exam are going to have some family resemblance to this, because this basically puts everything you know about generating functions into one question and gives you a chance to use the negative binomial expansion as well. So we've got 4 dice. We add up the numbers. And the first question is to write down the generating function for 1 die, which we've done many times before, and for 4 dice. So for 1 die, well, there's a probability of 1/6 of each of the outcomes. And since the smallest number that can show up is a 1, we have 1 power of s in everything. That's a perfectly correct answer, but since I know what I'm going to do with this, I'm going to go right ahead and write this as s over 6 times 1 minus s to the 6th over 1 minus s. Let's give that a name, say g1 of s. And then for 4 dice, it's easy. This is where the generating function pays off. Generating function for 4 dice is s to the 4th over 6 to the 4th times 1 minus s6 to the 4th divided by 1 minus s to the 4th. Now we want to calculate the probability that the sum on the 4 dice is 11, and the way to do that is to take advantage of the fact that the answer to this question is just the coefficient of s to the 11th when we write this out. So all we have to do is expand everything and identify all the terms that have s to the 11th. This being a final exam where time is at a premium, there are only 2 such terms. So we've got s to the 4th over 6 to the 4th times 1 minus s to the 6th to the 4th. That's 1 minus 4 s to the 6th. The next term is x to the 12th, so it doesn't matter. And then we've got to do 1 minus s to the minus 4th. Now, I'll tell you, I actually went to the last page of the exam and checked the statement of the negative binomial theorem to make sure I had this exactly right. It starts out 1 plus 4s, which is actually 4 choose 1 s. Now, there are a whole bunch more terms. This, and this will give me s to the 11th. The only other way to get s to the 11th, though, is s to the 4th here and an s to the 7th here. And actually,
should be 4 choose 3, right?
Yeah. It's 4 choose 3 or 4 choose 1. There are 2 equivalent ways of writing this out, but the simpler one always has the same symbol on the bottom here. So we've got something choose 3. 1 plus 3 is 4. 7 plus 3 is 10. So there we go. And the coefficient of s to the 11th is 1 over 6 to the 4th times, well, we've got a term with a plus sign, which is 10 choose 3 times s to the 11th. And then we've got a term with a minus sign, which is 4 times 4 choose 3. That's absolutely correct, and it says you may leave your answers in terms of binomial coefficients and powers of 6, or you may express it as a fraction in lowest terms with a denominator of 162. I would say, faced with that situation, I'd say, I'm going to go through, I'm going to work the rest of the exam, but one of my top priorities after I've answered every question is to come back, simplify this answer, and check that the denominator is 162 once I get it into lowest terms. So what have we got? 1 over 6 to the 4th times 10 times 9 times 8 over 3 times 2. That's a 3. That's a 4 minus 16. That's 104 over 6 to the 4th. And this is divisible by 8. That's 8 times 13 over 3 times 3 times 3 times 3 times 2 times 2 times 2 times 2. 3 of the 2's kill the 8. And what do you know? 13 over 164, which is also a correct answer, and particularly easy, 162, excuse me. Particularly easy to grade because someone's highly unlikely to get that by accident. Okay. Questions about this one? No? Then I'll do the next one. Okay. The next one is a baseball bonus question, but it's entirely equivalent, for example, to the question, you find a casino where you automatically win your bet if 0 comes up on the roulette wheel, so the odds are in your favor. you start with a certain amount of money. What's the probability that you will go broke in the course of the evening as a function of the number of dollars you start with? Here we have a question where the event that terminates things is on the upper end. The deal is we've got a baseball player who, like all baseball players, has a smaller probability for getting a hit than for making an out. And the deal is they will keep a running total as the season goes on of hits and outs. If at any point he's got 2 more hits than outs, he gets a big bonus. Clearly, this is going to happen early in the season, if at all. And to get you started, I've asked you to show all the ways that the player can earn the bonus after precisely 4 trips to the plate. This will encourage you to think of it as a random walk. So the question is, what's the probability of reaching level 2 for the first time after 4 steps? Well, one way to do it is like that. In fact, you have to end up with 2 hits, because if you don't have 2 hits as at bat 3 and at bat 4, he would have got there earlier. The other possibility is an out followed by 3 hits. So there are 2 ways of doing this, and the probability of this event is equal to 2, because there are 2 ways of doing it, times the probability of either of these, and each of these involves 3 hits, which have a probability of 1/3, and 1 out with a probability of 2/3. So we put this together, and we get 4/81. Everyone in agreement with me so far? Okay.
I have a question.
Yes.
Why couldn't you go? Oh, I see. If you went up and then
you can't
came
go
back.
straight up, because that would mean he gets the bonus after 2 times to the plate. This is just to get you thinking. There's some probability, in fact, 1 chance in 9 that he will win the bonus after 2 times to the plate. Then there's this probability you'll win it after 4 times to the plate. And if the final answer you get is not larger than the sum of those 2 things, you'll have done something wrong. Okay, this is almost exactly like the one I did in lecture and that you've had a bit of chance to practice with on the homework. This would have made a nice quiz question, but there wasn't a quiz to put it on, so it's showing up on the final. But it's easy to write lots and lots of questions like this, and I think this is an important enough idea that I want to encourage you to get this technique down pat so you can apply it in different situations, because as done abstractly with symbols rather than numbers, both in lecture and in the book, it's a little bit hard to swallow, whereas fundamentally it's really quite easy. So we want to use conditional probability. And we want a condition on whether the first at bat is a hit. So F sub k is the probability that he gets the bonus if he needs 2 excess hits in order to get it. Well, what can happen when he goes up to bat for the first time? He could get a hit, which happens with probability 1/3, and if he gets a hit, then he's only 1 short of the bonus. So the probability of going on to win the bonus is now F sub k minus 1. More likely, he will make an out. Now he has to get k plus 1 excess hits in order to claim the bonus. So this is F sub k plus 1. So that's the recurrence for this. And now we have to solve this. And the way you solve this, though I basically told you how to do it in the problem, is to know that there are always two solutions of the form x to the k. So let's plug in x to the k for f sub k, x to the k minus 1 for f sub k minus 1, x to the k plus 1 for f sub k plus 1, and now factor out x to the k minus 1. So we have x equals 1/3 plus 2/3 x squared. And if I write this in more conventional form by multiplying through by 3 and collecting terms, I get 2x squared minus 3x plus 1 equals 0, which factors into 2x minus 1 times x minus 1 equals 0. So the two possible solutions to this are x to the k where x equals 1, that is a constant, or x equals 1/2. And the general solution is that f sub k is a linear combination of the two, a times 1 to the k, or just a, plus b times 1/2 to the k. Now the boundary conditions here are simpler than any we've dealt with. Probabilities cannot be greater than 1, and furthermore, the probability that he would be able to win this bonus if he needed 10,000 more hits than outs is 0. So we know that this quantity has to approach 0 as k approaches infinity. And the only value of a that makes that possible is 0. So the answer is just a constant times 1/2 to the k. But if it takes 0 excess hits to win the bonus, he's already got it. So b has to equal 1. And the solution is f sub k equals 1/2 to the k. A surprisingly simple result in the case given. F sub 2 equals 1/4. And I defy you to get that simple answer by looking at this problem unsystematically and trying to sum an infinite series. There may be a way of doing it, but it certainly isn't simple. Catherine, question?
I missed what you said when how you get b equal to 1.
I get b equal to 1 because I know that f sub 0 equals 1. Right? If he gets a bonus the first time he has equal numbers of hits and outs, he can claim his bonus right at the start of the season. So the probability of getting the bonus is 1 in that case. So there really are two boundary conditions. One boundary condition is that this quantity starts at 1 for k equals 0. The other boundary condition is that it approaches 0 when k gets very large. Yeah, Dana?
Maybe I'm picking nits, but it seems like there's 3 solutions for x, one of which is non-trivial, the other one being x equals 0.
No, x equals 0 doesn't solve the equation. X equals 0 is not a root of this quadratic.
But it is of the one above, because you divided out x to the k minus 1. And it does look like it solves the original.
Oh, so you're saying a trivial solution to this, which I lose, is, you're absolutely right. A trivial solution to this recurrence is that f sub k is 0, and that fails to satisfy the boundary condition
But it
that
seems like that is just as good a trivial answer as x equals 1 being the other. Essentially trivial.
yes, I would say if you wanted to
Useful
say
one.
x could equal 0, 1, or 1/2, and since you only wanted 2 of them, I'd give you 0 1/2. I will accept that for full credit.
You need 2 linearly independent solutions to have a full general solution.
That is true. In other words, Dana's answer, though technically correct, has the problem that in most problems of this sort, you won't get the right answer because you need the solution with x equals 1 to fit the boundary conditions. Okay. Speaking of trivially correct answers, I haven't got to tell my helicopter story, have I? Okay. This one's so good I like to use it in every course. The story is that there were some people flying in a helicopter over the state of Washington, somewhat north of Seattle, on a terribly cloudy day. And their navigation system failed. They had no idea where they were. And the pilot said, well, look, the only thing I can think of doing is we'll descend through the cloud cover, hope we can see someone on the ground and ask them. So they descended through the clouds. They saw this big industrial complex surrounded by a parking lot, and there was someone standing outside, and they yelled down to him, hey, can you tell us where we are? And he yelled back, yes, you're in a helicopter. And the passenger said, fine, I know exactly where we are. The pilot said, where? He said, we're over Microsoft Technical Support Headquarters. How did you know that? Well, the answer was technically correct, but conveyed no useful information. Okay, next. Okay, here is a catch-all question involving intersections, unions, complements, De Morgan's theorem, and fundamentals of probability. And the main skill that's needed is to take events described verbally and convert them correctly into sets. So we've got a random 4-letter word that's posted on a website, and certain properties of this word, namely events that we can assign probabilities to. And what we're given is that the event starts with a consonant, happens with a probability of 0.8, we're also given event B has probability 0.3, and that ends with a vowel. And might be worth noting right away that the probability of B complement is therefore 0.7. That's the probability that it ends in a consonant. And finally, we're given one more obscure piece of information. Now, we all know there is a 2-by-2 grid that can be made out of these things. And what you need is basically 3 pieces of information, because the probability that something happens is always equal to 1. That's your 4th piece of information. So the extra event for which we're given a probability is event C. That has a probability of 0.6. It begins and ends with a consonant. Okay, there are a large number of ways to skin this particular cat, and I'll show you 2 or 3 of them, all of which, of course, lead to the same answer. The first one is express event C in terms of events A and B, well, that's pretty easy. Event C is an intersection of event A and event B complement. That's an easy 2 points and a good start for later on. Next question. Are events A and B independent? Justify your answer, which means that simply writing down no does not qualify for good full credit. Probably the easiest way of doing this is to consider the two events A and B complement, since we have the probability of A intersect B complement. Probability of A intersect B complement is equal to 0.6. The probability of A times the probability of B complement is 0.8 times 0.7, which is 0.56. So the probability of the intersection of the two events is different from the product of their probabilities. And wait a minute. Yeah, that's right. Okay. And they're not independent. Here's another way of doing it that is equally good. You can work out the probability of A intersect B. That's equal to the probability of A minus the probability of A intersect B complement. Because if A occurs and B complement doesn't occur, you've got the probability that A and B both occur. Probability of A is 0.8. This probability is 0.6, which is 0.2, but the probability of A times the probability of B is not 0.2. So they're not independent. Okay, next question. Event D is that the word has a consonant at the beginning, at the end, or both at the beginning and at the end. I stated as a general rule that whenever I say or, I mean or in the sense of union, but I didn't want to take any chances here of someone misinterpreting this, so I spelled it out in detail. Express this event in terms of A and B. Well, that is the union of starts with a consonant and ends with a consonant, A union B sub C, and we can calculate its probability by inclusion-exclusion. That's P of A plus P of B complement minus P of A intersect B complement, which is 0.8 plus 0.7. And how convenient, we're given A intersect B complement as an event with specified probability, minus 0.6. That's 0.9. Okay, last question. If you know that today's word ends in a vowel, what's the conditional probability that it also begins with a vowel? So we want to know the probability that it begins with a vowel. That's event A complement. Given that it ends with a vowel, probability B. And that is, of course, the probability of the intersection, A complement intersect B, divided by the probability of B. The easiest way to do this is to note that this event is the complement of event D. That is, if you spot the chance to apply De Morgan's theorem that the complement of a union is the intersection of the complements, you can say this is the probability of D complement divided by the probability of B. The probability of D complement is 1 minus the probability of D, and you get 1/3. There are numerous other ways of doing this, which are a little more long-winded, all lead to the same answer. But if I had time to kill at the end of the exam and wanted to check this, I think what I would do is to fill in this grid to make sure that everything checks. We've got the probability of A intersect B complement is 0.6. The probability of A intersect B is 0.2. What else do we have? The probability of A complement intersect B is 0.1, and therefore the probability of A complement intersect B complement must also be 0.1. So that's a way of checking everything. Questions about this? Okay. This next one is very seasonal, since we've just passed Epiphany Sunday, and this is actually a true story. The Elizabeth in question is Elizabeth Windsor, the long-suffering director of Christian education at my church, who lets me teach all these crazy courses. And the first one I taught was what every Christian should know about quantum mechanics, which she passed on when I said that you needed to know a little bit about imaginary numbers, and she said she'd never understood imaginary numbers. And then the next time I did faith, probability, and Bayesian inference, that gave rise to the Bayesian Bible. And for that one, she said, well, she'd never really been very good at fractions either, so she was going to pass on that one. Nonetheless, I walked into church, and she'd had the kids bake this stuff called Three Kings cake, and the tradition for Three Kings cake is you bake stars into some of the pieces, and I think the deal is if you get a star, you have to bake the cake next year or something like that. But she was worried, since I didn't know about these stars, that I was going to break a tooth, and I picked it up and said, hey, look out, Paul, some of these have stars baked into them. Would you like a different one? Elizabeth, that's a Monty Hall problem. So here it is, the Three Kings Monty Hall problem. And because it's a Monty Hall problem, we know that after we've worked it all out very carefully, there's going to be a simple check based on the fact that I have a certain probability of having picked up a star in the piece of cake that I chose initially, and that probability is not going to be changed by whatever Elizabeth, acting like Monty Hall, is going to do. So this is question 7 now. And part A says, when the cake was baked, what is the probability that piece 1 had star S1 and piece 5 had star S2? Well, there are at least 2 ways of doing this and getting the right answer. Probably the simplest is to say there's one chance in 5 that piece 1 has the first star in it, and since the deal is the 2 stars have to be in different pieces of cake, the remaining star has to be in one of the other 4 pieces because there are precisely 2 stars. So 1/5 times 1/4 equals 1/20. Another way of doing this, which is more in tune with what's going to follow, is to say, if we take two distinguishable stars and three blanks represented by x's, there are 5 factorial ways of putting those 5 objects into 5 pieces of cake. There are 3 factorial ways of permuting the 3 objects that are not stars, and 3 factorial over 5 factorial is also equal to 1/20th. Another way of doing this is to say, look, there are 20 pairs of stars, and the probability that one specific pair, there are 20 ordered pairs of stars, and the probability that one specific ordered pair, namely number 1 and number 5, will show up is 1 in 20. Okay, the second one also for 1 point. What's the probability that the 2 stars were in piece 1 and piece 5? And the answer is twice what you got before, because you could either have the situation described, star S1 in piece 1 and star S2 in piece 5, and you could also have them the other way around. I've used this on exams before, but this is really a better homework problem than an exam problem. It's a little bit too didactic. If you have never heard of the Monty Hall problem and keep your wits about you, you're going to end up with the right answer on this one because it leads you through all the steps of the reasoning, which is a great thing to do on homework, slightly questionable thing to do on a final exam. Okay, event B is the smallest available star was in piece 5, and the deal is that Elizabeth chooses the smaller of the 2 stars if she has a choice. So now we have to make a table of all the ways this can happen. There are 20 outcomes for the positioning of the stars, and there are 5 of them that correspond to event B. First, there's this one. And then there are 4 more like that, where star S2 is in piece 5, but star S1 is in one of the other pieces. And finally, there's the case where...
Shouldn't it be the other way around, where S1 is in 5 and S2 is in the other?
Yeah.
It doesn't matter, but according to the rules of the problem...
Yes, it does. You're absolutely right. As I've specified, the smaller star is called S1. And finally, there's the case where S1's in the piece that I've picked up, so the only star that's left is the large star, that's S2, and Elizabeth has to break open this piece of cake to show it to me. And so the probability of this event B is equal to 5 over 20, which is 1/4, and that's quite reasonable because there's nothing fundamentally different about the 4 pieces of cake that I don't have. Numbers 2, 3, 4, and 5. Elizabeth has to break one of them open, and therefore it's a reasonable check that if you pick one of these more or less arbitrarily, there's 1 chance in 4 that that's the one she cracks open. In fact, I think that's a perfectly legitimate way of getting the correct answer. Okay? That was part.
The last one, that I guess the example where in your last one where the large star is in 5.
She she's playing by the Monty Hall rules.
Right.
She's not allowed to break open my piece of cake.
Right.
And given a choice, she always reveals the smaller of the two stars.
Right.
But in the case where I've got the smaller star, she has to reveal the large one. That's the same as the case where Monty Hall has to reveal the older goat because the younger goat is behind the door that I picked.
Right. I guess I'm trying to understand that in connection with the language that's in the question, because that says the smallest one was in piece 5.
No, the smallest available one.
Oh, okay.
Okay?
All right. Yeah.
Yeah, she has to
of
pick
course. Okay.
from the 4 pieces
Yeah.
of cake that I'm not holding. She has to take the one that has the smallest star. An equivalent formulation of this problem is
The way you did.
she picks at random
Yeah.
if she has a choice. But I have found the problem is much cleaner if you have some criterion like smallest or oldest for choosing between them. I should also say, with the sole exception of the Christine's random dessert problem, where Shay and Marty swap one place, every Monty Hall problem I've ever heard of you can do in your head once you catch on. And the funny thing is, given the debate over this problem, the secret of getting these right is the obvious answer is always correct. I was explaining this problem. I got together with some former speech recognition colleagues last week, and I was explaining this over dinner. And I had an email from the former director of foreign marketing, and he said, "We've been discussing nothing over dinner for the past few days, but that problem you explained last Friday night, and I'm pretty sure I understand it, but how do I answer a person who says such and such?" So I'm just going to send him back the notes from this course about the problem and hope that satisfies him. Okay, what have we got? We got part D now. Part D is event A is Paul has a star in piece 1. Given that event B has occurred, determine the conditional probability of A. So that's the probability of A intersect B divided by the probability of B. And the probability of A intersect B is equal to 2 out of 20, because here are the two situations where Elizabeth cracks open piece 5 of cake and Paul has the star. The probability of B is 5 out of 20, and that's 2/5. And that has to be right because there are 2 stars. Paul picks one of 5 pieces of cake. He has 2 chances in 5 of having a star in the cake that he's got. And since Elizabeth is playing by Monty Hall's protocol, that's Sturzaker's term for this, that probability doesn't change. So this answer has to be 2/5. And the last question is, if Paul exchanges piece 1 for piece 2, what's the probability that he then has the star? Well, that would mean that he has the star only in one case out of those 5. So for part E, 1/10 over 5/10 is equal to 1/5. And now here's the shortcut way to do this in your head. This always works. You say, okay, there are 5 pieces of cake and 2 stars. Paul has 2 chances in 5 of ending up with a star. The other 4 pieces of cake are strictly equivalent to one another. Elizabeth cracks one of them open. Okay? There's a 3 chances in 5 that the star is in one of the 3 unopened pieces of cake. There's nothing to distinguish among those 3 unopened pieces of cake, and therefore the probability of 3/5 that Paul doesn't have the star has to be divided among those 3 pieces of cake, giving you an answer of 1/5. So this asks you for a lot of interesting calculations, by the way, but if you're a Monty Hall veteran, you know what the answer is by using shortcut and perfectly legitimate techniques. Any questions about this? That even suggests maybe one could write a Monty Hall multiple choice question. Okay, next one. Well, we haven't had a binomial theorem question yet. An unprepared student takes a quiz consisting of 4 multiple choice questions, each with 3 possible answers. Knowing nothing about the subject, the student answers each question by rolling a die to choose randomly among the 3 answers, and so has a probability p equals 1/3 of getting each question correct. So this question mixes conditional probability and the binomial distribution. It's similar to the Kabul-Kibers question, which I put on the homework, though not quite as imaginative. What's the probability that the student gets precisely 2 correct answers? Well, this is straight binomial. He's got to get 2 right answers, probability 1/3 squared. He's got to get 2 wrong answers. Probability for that is 2/3 squared. And then there are 2 of the 4 questions that he gets right. So there are 4 choose 2 ways of selecting the pair of questions he gets correct. And this is 6 times 4 over 81, or 24 over 81, which some folks might simplify to 8/27, though I do not take off if you neglect to reduce your fractions to lowest terms. Okay, what's the probability that the student gets fewer than 2 correct answers? If I've read part C first, I realize that I'll need the probability for 0 correct and 1 correct individually. So the probability of 0 correct is 2/3 to the 4th. That's 16 over 81. And the probability of getting 1 correct is 4 choose 1 for the question the student gets correct, times the probability of 1/3 of getting it correct, times 2/3 cubed for getting the other 3 wrong, and that's equal to 32 over 81. And the sum is 48 over 81. Now, at this point, I would say, since I still have an hour and a half to work on this exam, although nobody asked me what's the probability that you got 3 or 4 correct, it would be folly not to work out those probabilities and check that everything sums to 1. So, given enough time to do it, the probability of getting 3 correct is equal to 4 choices for the one he gets wrong times 1/3 cubed times 2/3, and that's 8 over 81. And the probability of 4 correct is equal to 1 over 81. And my check is that 1 plus 8 plus 48 is 57, plus 24 is 81. So I've worked out the whole binomial expansion of 1/3 plus 2/3 to the 4th, and everything checks. Okay, the last question is, suppose the student gets an email saying you failed the quiz, and he asks, oh goodness, what's the chance that I got them all wrong? The answer is part C. The conditional probability of 0 correct given 0 or 1 correct is equal to the probability of 0 divided by the probability of 0 union 1, if you don't mind my notation, and that's 16 81st over 16 81st plus 32 81st, which is 1/3. Questions about this? Hi, Chris. I got 5 minutes left, and I've got 2 questions, so I guess we'll have to run over onto a second tape. Why don't we break now then, and I'll do the last 2, and Chris can pass back the homework. Chris, whom the distance learners may never have seen, will explain what can be done by way of review. And you'll need the microphone.
I'll just need it for a second. Okay. Hi, everybody. The review is going to be on Monday. I know that's Martin Luther King Jr. Day, but let's see if you can make it. It's 5:30 to 7:30. For the first hour, I'll basically present problems, and I'll present solutions and topics that I think everybody had trouble with on all the different homeworks. And then for the second hour, I'll take your questions. I'm handing back all of the homework today, so you can look through it. So it's 5:30 to 7:30, Monday the 16th, in the Science Center, room 109. Does everyone know where the Science Center is?
Science Center.
If you don't, you can go to www.map.harvard.edu and
What were
put
the times again, Chris?
5:30 to 7:30. So it's on map.harvard.edu. It's slightly northeast of here.
Okay. Okay, I'll move on to question 9. I should say I'm going to get through all these questions in about half the allotted time. My rule of thumb when I was teaching physics is if I couldn't do an exam 5 times faster than I was expecting the students to do it, it was going to turn out to be too long. And when I actually sat down to scribble out my answers to this one, it took me a little bit less than half an hour. So I think that's about right for giving people 2 to 2.5 hours. In spite of its paper consumption, this is a perfectly reasonable 2-hour exam. And I think there will be people who are done after 2 hours, but I think 2.5 hours should give everyone all the time they need to get everything they know down on the paper. Okay, question 9. Oh, this looks like a random walk and bijection between paths question. And it is a reasonably easy one of this genre, provided you understand the general strategy and have seen it before. By establishing a bijection between paths, prove that the number of, quote, non-zero paths that start in level 0 and do not return to level 0 during 2m steps of a simple random walk is equal to the number of non-negative paths that start in level 0 and do not visit any negative level during 2n steps. And then, because I want a single right answer to grade, I've asked you please to associate non-zero paths that stay positive with non-negative paths whose last step is up. And that is actually a useful reminder about how to do this. So, now, I would say if a clever person was going to get one thing wrong on this exam, the obvious error to make is to neglect to do the bijection in both directions. That is, you have to show that this function is invertible. It's rather trivially invertible, but you nonetheless have to point this property out in order to show that you have a bijection. So let's start with a path that is always positive. It has to go up, and subsequently it can touch level 1 again, but it can never go down to level 0 because it wouldn't be a non-zero path if it touched 0 again. And all we have to do is treat this as the start of our non-negative path, and then tack on a single up step at the end. So this will go there. Yep.
I was just thinking, the way you drew it, it looks like you have one step and then the rest, basically.
Yes, I've done something
with-
misleading, Anna, haven't I? What I've done is it has to be at least in level 2 on the next last step. And I think there's something to be said for going right ahead and doing the first part of part B, which is show exactly what this bijection is in the case where you have paths with 4 steps. So we have U, 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 U goes to U, 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 U. That's easy enough. There are going to be 3 other all positive paths. Let's do U, 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 D. And this says take U, U, D, and tack on the U. And finally, we've got U, U, D, U, which goes back to level 1, but never to level 0. And that's U, D, U, and we tack on a U. So that matches up 3 of the non-zero paths, the ones that start with an up step, with 3 of the non-negative paths. Now to finish off part A, the other possibility is that the first step is a downward step, and we've got an odd number of additional steps. Sorry. Odd, 5, which means that if the path is always negative, it has to end up in level -2. And the deal here is you take this part and flip it, and now you have a path that is never negative, and you tack on a downward step. So let's do these. D, 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 D goes to, we've got to flip this over, turning it into U, 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 D. We've got D, 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 U. we flip the last three steps over, getting U, U, D, followed by D. And we have D, D, U, D. Flip the last three steps over, U, D, U, followed by a final D. None of these can match any of these because these all end up with an upward step and these all end up with a downward step. And the rule for inverting this is simply, if you want to invert this function, look at the last step. If the last step is an upward step, start with an upward first step, and the rest of the path makes it stay positive. If the last step is down, start with a downward step, and then the earlier steps with U's interchange for D's and D's for U's will guarantee you a path that stays always negative. I stated that rather informally, but that would have been perfectly enough for full credit. Dana, you have a question?
To make sure I got this wired, if
Yep.
you remove the admonishment about uniformity of answers in the question, can you swap
Yes,
ups
you can.
and downs? In the
Absolutely.
last?
Absolutely. It would be equally correct to say we'll tack on the reverse of the first step. That's invertible in the same way. So this is not a unique bijection. It's just one of at least two possibilities. And there are probably other ways of doing this too, where you split off the last step. And I'm wise enough not to leave these questions too open-ended, because then, if there are 16 correct answers, then I have a very hard time spotting any wrong answers. I have to go and check everything. Whereas this way, everyone should get the same table here. Other questions about this? Okay. We've had no munchkins. Oh, and here are the munchkins, the Senate munchkins. Question number 10 with the Homeland Security Committee. Okay, what's the deal? We've got 6 members on this committee, 4 Republicans and 2 Democrats. And in this particular case, Thomas and Catherine don't have equal size bags because there's a 2-member Homeland Subcommittee and there's a 4-member Security Subcommittee. So the first question that we want to ask is, what goes in the denominator? How many ways are there of dividing 6 senators into a subcommittee of 2 and a subcommittee of 4? And the answer is 6 choose 2. 6 times 5 over 2, which is 15. So there are 15 pairs of senators that could be chosen to serve on the Homeland Committee. And all we have to do is count up the number of ways of doing that with no Republicans, 1 Republican, and 2 Republicans. So we'll do event A0 first. Event A0 is the case where there are no Republicans on this committee. Split strictly along party lines. There's only one way of doing this. There's absolutely no choices involved. So the probability of this event is 1 over 15. What's the probability of getting 1 Republican on the Homeland Committee so that the makeup looks like this? The easy way to answer that question is to say, if you're going to do this, there are 2 choices for your Democrat, and there are 4 choices for your Republican. So there are 8 ways of selecting a pair consisting of 1 Republican and 1 Democrat. The probability of that one is 8/15. And finally, if both members of the Homeland Committee are going to be Republicans, we've got this situation. In this case, we choose 2 out of the 4 Republicans. That's 6/15. And I would say there's precious little point in reducing this to lowest terms, because the check now is 1 plus 8 plus 6 equals 15. So the probabilities sum up to 1. If I only asked you 2 of these 3 questions and you had any time on your hands, you would have been very well advised to work out the 3rd probability independently, just so you have this check of summing to 1. Chris, a comment? Okay, we turned the page, and it's conditional munchkins. A terrorist kidnaps a randomly chosen senator from the Security Committee and ascertains that this senator is a Democrat, event B. In other words, Catherine pulls a munchkin out of her bag, and it's a plain one. Now, there are 2 ways of doing this, and I'm going to show you both of them, because in a question like this, again, if you have time to spare, there's no harm in doing the question both ways. Remember, one way of doing a conditional probability question is to use the formula P of A given B is P of A intersect B divided by a phi of B. But you can also do the question by saying, well, let's consider event B has happened, and let's just do by straight counting the probabilities for event A under those circumstances. And you may recall the problem where your opponent had a poker hand with 2 exposed cards, both of which were aces, and you had to calculate the probability that your opponent had 4 aces. The way of saying how many ways are there of choosing the remaining 3 cards to give 4 aces was actually a much shorter way of doing that problem. So sometimes one of these methods is more efficient, sometimes the other is more efficient, and if you do them both and they both give the same answer, you can be really quite sure that you're correct, because they lead to somewhat different calculations. Okay, so let's do D, E, and F first, the straightforward way. Well, what's the conditional probability given that a senator kidnapped from the Security Committee was a Democrat, that there are no Republicans on the Homeland Committee? That probability is a big 0, because in that case there's nothing but Republicans on the 4-member committee, and you can't kidnap a Democrat from it. So the conditional probability that both Democrats were on this committee, given that we already know that there's a Democrat on that committee, is 0. That was easy. Now we should get 2 probabilities that sum to 1. So we now want to know what's the conditional probability given that a randomly chosen member of the Security Committee turned out to be a Democrat, that there's 1 Democrat and 1 Republican on this committee. So we have a situation like that. Well, here's one way of doing it. You can say that's the probability of A1 intersect B over the probability of B. And this is the probability of A1, which we calculated, times the probability of B given A1 over the probability of B. the probability of A1 worked out to 8/15. And if A1 has occurred, then there are 3 Republicans and a Democrat on this other committee, and if you snatch one of them at random, not knowing the person's party affiliation, you got 1 chance in 4 of getting the Democrat. There are long-winded ways of calculating P of B, but a perfectly good way of calculating P of B is to say these senators were distributed randomly between the 2 committees. The Democrat was snatched randomly from the committee that he's on. There are 2 Democrats and 4 Republicans, so there's 1 chance of 3 in getting a Democrat. So that is 2/15 over 5/15, which is 2/5. I'll show you an easier way to do this in a minute. Now, at this point, you could say the probabilities have to sum to 1, so this has to be 3/5, and I can't mark you wrong for that. I can say you exhibited bad judgment and were lucky, because you can also do this directly, and then you get a free check. So this is the probability of A2 times the probability of B given A2 divided by the probability of B. Probability of A2 we said was 6/15. The probability of B given A2, well, A2 means we got 2 Republicans here, 2 Democrats, 2 Republicans there. Pick one at random. There's a probability of 1/2 that you get a Democrat. Divide by 1/3, and you got 3/15 over 5/15 or 3/5, and what do you know, these sum to 1. Now, here is another way of doing this. Another way of doing this is we can say, fine, we know that one of the members of the Security Committee is a Democrat, and then the question is simply, how many ways are there to divide up the remaining 5 senators, of whom 2 are Democrats, and of whom 1 is a Democrat and 4 are Republicans. So another way of doing this is to say, if you take 4 Republicans and a Democrat, there are 5 choose 2, which is 10 ways of distributing them up, and the probability that you get 1 Republican over here under those circumstances is the number of ways of selecting 1 Republican to go with the Democrat. There are clearly 4 Republicans you can choose over 10, which is 2/5. And in a similar manner, for F, you can say the number of ways of getting 2 Republicans over here is, there's 4 choose 2 ways of getting a pair of Republicans divided by 10. That's 6/10 or 3/5. In this particular case, I think that's slightly simpler, but I prefer to use it as a check anyway. Okay. Have I made it all seem too easy? I mean, apart from the fact that 99% of the people in the world can't do these questions, it's really not that difficult. And anything on here that struck you as a curveball? I try not to put curveballs in an exam, so the answer I'm looking for is 0. Yeah, Dana?
The wording on the Monty Hall
Yeah, that's the
problem
only-
might have been slightly improved by reminding us of the protocol in question.
Yes, okay, that's a good point. I think I'm actually going to retire that Monty Hall problem anyway. Sorry, I'm not going to retire it. I'm going to put it out to pasture as a homework question because it's a nice question, but it's not a particularly good exam question. And I'll tell you why it's not a particularly good exam question. You've undoubtedly encountered this phenomenon in other courses. If you present the easiest case of something in class, then when exam time rolls around, you end up having to invent a harder question because you've already used up the easy one. And in the other course I'm teaching this term, Math 152, which I'm going to be, Anna took the summer school version of this, but I'm going to be offering a version in the extension school in the spring with the probability left out to make it fit. There's a lot of attention paid to 2x2 matrices where the entries are drawn from finite fields, which might have 2, 3, 4, or 5 elements in them. And I actually planned ahead on this. In the course, I do exhaustively the case for finite fields with 4 elements and finite fields with 5 elements, leaving the finite fields with 2 and 3 elements for homework and exam questions because they're computationally much simpler. And in a sense, what I probably should have done with Monty Hall is present a problem like this in class and then leave the really simple case with 3 doors as a quickie homework question. Yeah, Robert?
Back in, I think it was question 4, where you have that way of expanding the fourth power generating function.
Yes?
How do you get that, the finite and the infinite? The two factors that you, if I can find it, yeah.
Oh, how did I...
You separate.
Okay, so the question is, how did I get the expansion of...
binomial.
It's a mix of the... So the question is, how do I do that?
Yeah.
And the answer is, I think of it like this. And, spring this on people who've never seen it before. It's probably a nice question for this Putnam mathematics competition, where they ask lots of straightforward but almost impossible questions to try to figure out who are the brightest young mathematicians in the whole country. If you're really clever, you look at this never having seen it before and say, oh, if I write it like this, I can multiply the regular binomial expansion by the negative binomial expansion, but you've been shown the trick. Okay, so now this one, and at this point, I say I already had 4 powers of s over here. The next term is going to involve s to the 12th, and since I'm only being asked for the coefficient of s to the 11th, that can't possibly be relevant to anything. That's why I write plus dot dot dot. There'd be nothing wrong with writing it all out, but this is only an efficient method if you compute only the terms that are going to matter. If you compute all the terms, it becomes rather a pain. This one, I'll tell you what I did. Said, I can never remember this formula, and that's why I want to look at page 14. And on page 14, which will also appear on next week's exam, we have 1 minus q to the minus r equals the sum of r minus 1 plus I times choose r minus 1 over q sub I, or perhaps even better, looking at the line above it, you can see that it's 1 plus 3 choose 2q plus 4 choose 2q squared plus 5 choose 2q cubed, and therefore this one is going to be 1 plus 4 choose 3s plus 5 choose 3s squared plus, and now the only term that's going to matter, because I had an s to the 4th here, is the one in s to the 7th, which has to be 10 choose 3, s to the 7th. And it's true, this looks infinite, but we all know that once you get a number that's so large you can't throw it on 4 dice, all the coefficients beyond that have to be 0. I'm sure this could be proved directly, but I would say if you write down the proof for that, you've probably got a nice derivation of an interesting combinatorial identity. Other questions about the exam? Questions for me or for Chris about anything else tonight? Okay, well, I wish you all best of luck next week. I thank those of you who have faithfully come to all the live classes for your attention, your good questions, and your reactions that I hope gave me a good clue as to when I was being understood and whether I better say things again. And to those of you who are only on video, I hope you've enjoyed the course and you missed a chance to meet a really nice group of people in this room.